In this video, we're going to talk about the theory behind second-order linear differential equations. So what are we talking about? A second-order linear equation like this one is one where, well, it's second order, which means its highest derivative is 2. But what's key here is that the variables y, y prime, and y double prime, they all appear with just power 1. They're an expression with a coefficient. The coefficient might be some function of the dependent variable x. So, for example, p of x in front of the y prime, or q of x in front of the y, or on the right-hand side, f of x, which I think of as in front of the function 1. So you could have coefficient functions of the independent variable, but anywhere the dependent variable y and its derivatives appear, that is just to the power of 1. That's a linear differential equation. And then one final piece of terminology is that if the function on the right-hand side, the f of x, happens to be 0, then we call this a homogeneous second-order linear differential equation. So really what we want to figure out in this video is what is the theory that's associated with this class of differential equations. And the first thing, the classic theorem in differential equations, is an existence and uniqueness theorem. Indeed, anytime you try to describe a class of differential equations, so we're describing the class of second-order linear differential equations, it's useful to try to answer when do solutions exist and when are those solutions unique. And so this is one of a family of existence and uniqueness theorems. Indeed, it's going to be pretty much the same as the existence and uniqueness theorem that we saw for first-order linear differential equations. Okay, so what it says is I'm going to begin with a generic second-order linear differential equation. Doesn't have to be homogeneous. And I'm going to give it two initial conditions. So y at the value of a is what I'll call b naught, and y prime at the value of a is what I'll call b1. So what's different about this from our previous analysis of first order differential equations is I now have two initial conditions. One initial condition that's specifying the value of the y, and the other which is specifying the value of the y prime, the derivative. And indeed, in a generalization of the theorem to an nth order differential equation, you would have n different initial conditions here. So right now at the second order, we have two, one for y and one for y prime. Then the third thing to note is the conditions on the components. So p, q, and f all are required to be continuous on some interval that contains the value of a, that contains the spot where you're doing your initial condition at. And then the conclusion is that then you get a unique solution, that it both exists and it is unique. And more important than just that, it exists and uniques on that same interval I where the functions were nice. If the p, q, and f were continuous on I, then the unique solution also existed on I. So this is our existence and uniqueness theorem. So basically what we've learned is that a second order linear differential equation has the same type of existence and uniqueness theorem that a first order does. Wherever the functions are nice, then you get an existence and uniqueness claim. So while the existence and uniqueness theorem was pretty similar to what we saw and might have expected from looking at the first order case, what we're going to see next is something that is only really interesting to us in second or higher order differential equations. And this is called the principle of superposition. So I'm now focusing on a homogeneous linear differential equation. The right-hand side here is equal to 0. And what I'm going to imagine is that I have two solutions already, a y1 and a y2. Then you can take any linear combination of them, c1y1 and c2y2, any possible linear combination for any possible coefficient c1 and c2, and that linear combination is also a solution to the original equation. Previously, we might have talked about how if you have a solution, you can multiply it by any constant, but now we're saying we can take two different solutions, you multiply each of them by any constants, you add them together, then indeed that's going to be a solution. The proof of this is pretty straightforward, but I need a little bit of space, so I'm going to step away. What we're basically doing is we're taking that c1y1 plus c2y2 and we're plugging it into the differential equation. So we plug it in for y double prime, we plug it in for py prime, and we plug it in for qy. Then the next thing I need to do is actually take the two derivatives and actually take the one derivative. And this works out really nicely. For example, the c1y1 plus c2y2 double primed, well, the double prime just comes in. This is a property of the derivative. The derivative is a linear operator. And what this means is that the derivative of the sum is the sum of two derivatives, for instance, or the derivative of a constant times a function is a constant times the derivative of the function. So this just means I can take those derivatives, distribute them inside the brackets, and get expressions like y1 double prime, y2 double prime, and so forth. And then if I look at this expression, I notice that there's 3 terms that have a y1 in it, all multiplied by c1, and that there's 3 terms that have a y2 in it, all multiplied by c2. So I'm just going to group those terms together. Basically what I'm going to do is I'm going to have a c1 term, and that multiplies all the things that have a c1, which was a y1 double prime, a py1 prime, and a qy1. And then I'm going to have a c2, I'm going to bring that out, and all the things that have a c2 in it were y2 double prime, plus py2 prime, and plus qy2. But if I look at both of those expressions, well, those are just the original differential equation. The assumption is that both y1 and y2 solve the original differential equation. So if you plug them in, you're supposed to get 0. So what do I have? 0 plus 0, which last time I checked was 0. And so this proves that when you have a linear differential equation, it basically works nicely with what we call linear operator of the derivative, and so a linear combination is going to solve it as well. Okay, so we're making some progress onto our theory. We know that if you take y1 and y2, any linear combination of them is a solution as well. But I want to specify certain types of y1 and y2 that are going to be more convenient for our theory. And we're going to use the notion of linear independence. So I'm going to say that 2 solutions, y1 and y2, are linearly independent if they're not just a scalar multiple of the other. For example, sine of x and cosine of x are sometimes equal. However, they're not always equal. They're not equal on an entire interval. They're not just one as being like 3 times the other. In contrast, x squared and 2x squared, they're literally dependent now, because one is just twice the other. This, by the way, is very analogous to how we would define linear independence of 2 vectors if you have taken a linear algebra course. And indeed, you could also ask the question, what would it mean for n different solutions to an nth order differential equation to be linearly independent? And you can try to come up with the analogous concept for that. Again, linear algebra, if you've seen it before, will definitely help motivate that answer. So now we come to the real heart of the matter. And this is the following theorem. It says, let's consider the homogeneous case, a homogeneous linear differential equation. And let me suppose that I have 2 solutions to it, y1 and y2, that obey the property of being linearly independent, that they're not just a constant multiple of each other on an interval. Well, then I get the following thing. Any solution at all that you can come up with can just be written as the linear combination. This is much stronger than what we were just talking about with superposition. Superposition said you have a y1 and you have a y2, their linear combination is a solution. I'm saying more now. I'm saying any solution can be written as the linear combination of the y1 and the y2 if the y1 and the y2 are independent solutions. So this is extremely nice. Imagine you go and you compute 2 different linear independent solutions. And then I go and I find some completely different solution, some third solution. Well, it must be that my third solution isn't really new. It's just a linear combination of the 2 that you've already come up with. And so this solves a crucial sort of halting problem in differential equations. You could find one solution, then another solution, then another solution, then another solution. When are you supposed to stop? Well, this tells you. If you found 2 that are linearly independent, you've found them all. Every other one can be written in terms of the linear combination of those 2 different solutions. And again, this will generalize into the nth order, where if you have an nth order differential equation and you have n linearly independent solutions, then any solution could be written as the linear combination of those n linearly independent solutions. All right, so let's illustrate this principle with an example. This is a second order linear differential equation, a classic example, y double prime plus y is equal to 0. Now, I haven't told you how to solve this. I haven't given you any method yet, but I'm going to assert for you that 2 solutions are y1 is sine of x and y2 is cosine of x. 2 solutions that we previously argued were linearly independent. They're not just a multiple of the other. And at this point, you can at least verify that I'm not lying to you. If you take 2 derivatives of sine, you get minus sine plus sine is equal to 0, and likewise for cosine. So they are solutions. And thus, since they're linearly independent, we know the general solution to this differential equation is just c1 sine of x plus c2 cosine of x. If you knew your initial condition, you could then figure out the c1 and the c2, and you would have the existence of that unique solution that's guaranteed to us by the existence and uniqueness theorem. And now, the final remark I'm going to give you is that there is a definite weakness when you go from first order to second order differential equations. When we were talking about first order linear differential equations, what we had then was that there was a method to solve it that always worked. It was the integrating factor method. Indeed, the fact that we knew that there existed a unique solution was just do the integrating factor method. It always works. It always gives you a unique solution. That was the proof. And this is a general heuristic with differential equations, which is that as you raise the order of the differential equations, in this case we're going from first order to second order, it does make the methods more challenging and some of the ability to just answer everything in one swoop, which is what the integrating factor method did. It gave us an answer that always worked. And so one consequence of this is that for second order and higher differential equations, we often lose some of the more powerful general methodologies that always work no matter how it's written. And we'll have to focus our attention on differential equations written in a specific way and come up with a method for them when you've got sort of more restrictive assumptions. But anyways, we'll do that and more coming up in future videos.